Okay, let's get it started. Week 7, and I can't believe it's already halfway through the whole semester. So today we are going to talk about classification problems. But before that, on the screen, the whiteboard, I draw 3 circles. In my lab, people know I always draw 3 circles, put biology on the top, and the algorithm is one of the corner here, and then you have data. So as a student from a biology background, you probably have your problem defined, and you study liver, you study neurons, or you have your biology questions. So you have your hypothesis, and you try to find, say, what pipeline I can use, which algorithm I can use to solve my problem. And so this circle, you go that direction to search for algorithm, all right? And sometimes you have, okay, I will generate my own data set, and a valuable data set, apply some algorithm to solve my problem here. So the logic of the flow chart looks like this. But what I hope is after this lecture or this semester study, you probably can consider start your problem with algorithm. Okay, you abstract all the objects, the data points on your mind, and see how I can apply some of those operations I learned from this semester, and to see how can I transform or find a new way and design an algorithm to extract the information from the data to solve some of the problem in biology. Sounds really hard because you haven't coded anything yet. But how can I design algorithm? Is that possible? So today I'm going to show you some of this very basic operations you learned from PCA. For example, you know how to rotate the data points. But just repurpose this rotation for not showing the maximized variability within the data points, but show something else. So you can borrow that simple idea. You know how to design the rotation matrix. You know how to rotate your data points. But instead of, for example, to show the maximized variation among data points, you can see, okay, how can I show from a special angle to separate these 2 clouds of data separately? Okay, for example, you have 2 cell types you want to rotate to make them looks more separable rather than to show globally more variable among the data. You need some abstract thinking here, but to know the principle about those algorithms, to build that language in your talk with the data scientists, for example, you know normalization, you know transformation, you know rotation matrix. Sometimes you may mention eigen decomposition, eigenvalues. So when you talk with the data scientists, just using that language, but you know, okay, your ultimate purpose is try to solve the problem. You want to separate the cell, different cell types. You try to see whether you can separate samples from a patient, from a healthy individuals. Something like that, okay? I will give you an example in the middle of the talk, and your homework will be relevant to design a new algorithm on your mind, okay? To explain what your idea is, all right? Today we also fortunate enough to have Kagate Bar. He's from Turkey, and he's a visiting student in my lab. He's an expert in the neural networks. Okay, so he will give our lecture the next hour about the history of neural network development, artificial neural network on computer. Okay. It fits very well with today's topic because neural network is one of the most important algorithms in classification. So I'm not going to cover much of that. I will very quickly go through neural network, but I will introduce something else around the neural network to help you to do the classification. For example, KNN, K nearest neighbor, logistic regression, I will very quickly mention. LDA is the one I just mentioned. You rotate your data using the same way PCA is doing, okay? Using the rotation matrix to rotate your data. But your goal is different. It's not to separate all the data points, but to separate two groups of samples, two groups of data. I will mention naive Bayes method, and also there are some evaluation metrics or method we have to learn. Once you finish the classification, how can you judge whether the classifier you use is one is better than another? Okay. I will mention some of the classification tools in cell type identification, so annotation of cell type. This topic is very important in data science, in machine learning, because so many problems and the people are working on shield applications are classification method problems. So this is a supervised method. It's different from a clustering method, which unsupervised, you don't need to teach or tune the parameters, but it's just like your algorithm to separate the data into different clusters. But here, you need to label your data points into different clusters first. Okay, then you use this training data set to tune the parameters in the classifiers, and then you start to use your the classifiers have been set up and to apply to predict the membership or group IDs for new data points. Again, this is a two-step procedure, and you need to train the data, the learning step, okay? To the algorithm is learn how can set up the parameters to separate data points into different classes, and they have been labeled before given to the algorithm. So you know the answer and let algorithm to set it up to help you to separate those. And then you throw away the training data set and start to use real data set to test, to give the algorithm to let it to predict. Okay, another illustration. Label the training data. And sometimes you need some pre-processed steps to make this data clean. For example, you want to remove some less important features and noise. So this is feature extraction. And the vectors, vectors are data, right? Give to this machine learning algorithm, basically the classifiers. Then to train the data to learn this. From the illustration, is to learn what? To learn this separation line, okay? How can you put this line? This will be learned from the training data. So once you are done, you are ready to give this to the users. The users will have new data points, which was not in here, and gave to the algorithm. Algorithm will answer, okay, this data is belong to this group rather than that group, and what the percentage of confidence sometimes give you the answer. Many applications, and you gave a picture, for example, to this function. This function is a classifier function, classification. The function will take that object, learn the feature, and give you an answer. Okay, you have to train this function, of course. So this illustrates the procedure of training. You have to have a lot of pictures, a lot of data, okay? They have been labeled. In recent years, and the label, this image, is a very important step. You have to, the companies, for example, if they want to do a very good product to do this prediction, they have to recruit a lot of human beings to annotate manually those pictures. What that for is just create a large data set for as training. So you gave enough training data, extract information from the image, and learn the labels, and this is called the learned model, okay? This has been trained. Once finished, you start to test your results. This learned model we'll put here, okay? Is that clear? So you, on your mind, you probably want to replace this into different cells, okay? This is one cell type, this is another cell type. You can borrow the whole framework, say, I want to train my data after I manually label them, and next time I don't have to manually label the new data cells. And again, I just gave the cells to the classifiers and let it to do the job for me. We probably can try some of this in the computer session in Thursday, okay? On Thursday. With single cell data. So I want to quickly go through some major clusters of the classifiers, different categories. Logistic regression, naive Bayesian classifiers, and linear discriminant. And this perceptron is belong to the neural network, the foundation of individual neurons. So I will leave this to Kadaga, and he will talk more about those, and I will mention some of this. And this may, we may cover some of these topics next week, okay? Support vector machines. So this is the foundation of a neural network. You have a function in the middle to synthesize the inputs, and this is just multiplication of vectors. Okay, this vector weight multiplication for the features of your input data, and then take a sum. So pretty much like a dot product, and then decide what output should be. So this is one unit, but you linked with many units together and make a network. So this is one of the example, and I'll show you one of this individual neuron, okay? So those are the neurons have been linked together, and you have input to give to all the neurons, and information will synthesize and give to another layers of neuron. So within this operation, they all matrix multiplications. Okay, what we talk about the neural network at the end are the matrix multiplications. You have data, you multiply by the weight of the one layer's neurons, then the output become another matrix and put to next layer, and then you multiply it by another layers of neurons. So that's why from day one I say the matrix multiplication is so important in every single steps in those operations. So neural network is basically a series of multiplication between matrices. Okay, you pass on input of this, give to output. Output will become input for next layer. So you keep doing that until you reach to the last layer. Then you have a so-called activation function, and to decide this belong to which category. So I will leave this more for for our guest lecture speaker. Okay, so this is a cartoon for convolutional neural network. This is really good for picture information synthesis. So you learn the picture and do this convolution operation to translate or transfer the information from a picture into this new picture after scan the pixels, okay? Yeah, maybe I just quickly show you how this new convolution network is working. So the algorithm scan the input image using this sliding window. Okay, you can define the size of the windows. And then each time it will aggregate information under this sub-window and then extract that map to a new layer. So basically you transform information from that to a synthesized matrix, contains the information of original picture. So the algorithm will probably use different different parameters to scan your image in order to extract, for example, sometimes the more detailed information, sometimes the more global view of the picture. And after that, it create multiple synthesized data, then did information extraction to reduce the dimension, then make a pattern and to search against the training pattern to give you the answer, okay? Okay, so when we say machine learning, we mean more broadly so it's like a broad subfield in the computer science, okay? So, but the deep learning is more specific. It means you use neural network in the machine learning, but also this neural network have multiple layers. So machine learning is more than a classification problem, but deep learning, when you say deep learning, mostly you talk about a neural network with many layers. And the purpose for deep learning mostly is to do the classification. Okay, this is a very quick walkthrough to next classifier we are talking about. This is a so-called nearest neighbor, okay, KNN. Nearest neighbor is very commonly used not only for classification, but also to help you to move with small steps to reconstruct the global structure of your complex data sets. So how this works is this, you have data, and this is like 2D examples. You have a class A yellow points and class B purple points. laser point. So if you decide I'm going to use k equals 3, you only look at the nearest neighbor of 3 data points. The problem here is I will decide whether this new data point, this red star, belong to class A or class B. If I decide to use 3 nearest neighbor as my decision region or decision hyperparameter, so I will look at the nearest neighbor, 3 nearest neighbors. Okay, in this 3 nearest neighbor, 2 are purple, 1 is yellow, so I decide this should be classified as the purple. If I decide to use nearest neighbor k equals to 6, then I have to find the 6th nearest neighbor of this data point. In that case, I have 4 class A, 2 purple. I will assign this as a class A because majority of my neighbors are class A.
So
yeah.
Just randomly choose 6 or just you need to calculate the distance?
I don't think we have a way to calculate the k, so you have to provide the k for yourself.
You need to calculate the distance.
Yeah, distance you have to calculate.
Then you decide which 6 you choose for. You just randomly choose 6. The 6 point you just randomly choose?
Yes, I think you can decide yourself how many neighbors you want to use to decide the member. Decide the membership of your new data point.
How can you decide which 6 you choose?
Oh, you decide by look at the nearest distance.
So you need to calculate.
Yeah, you have to. That's right. So that's why our third lecture is about the distance, all kinds of distance. So you have to compute the distance between your data points. Yeah, you have to do this first. Okay, so yes, you're right. And then you know who are your neighbors, who is the nearest neighbor, who is the second, who is the third nearest neighbor. So that's why the way how to compute the distance between data points are so important. You have to compute it very quickly, and also you have to calculate using the right distance. Remember, we have a Euclidean distance, we have a Mahalanobis distance, we have a cosine distance. Okay? Yeah. And sometimes you want to weight your distance. What that means. So the neighbor, okay, although you have 2 neighbors in blue and 4 neighbors in yellow, but these 2 purple ones are relatively close to your tested data point. So you want to weight this distance higher when you assign the membership. You probably say, okay, this is so close that I gave a weight at 5, and this is so close I gave you 3, and this weight is also 3, but when you have so far away from each other, I only gave you 2 here, 1 here, 1 here. So although you have a dominant number of the yellow cluster neighbors, but because of relative distance, you can weight that down a little bit. So at the end, probably, if you gave the right weight, although you use k equals 6, you still classify this new data point into purple. Okay? So what's the advantage of this? This is a lazy algorithm, okay? No, You don't need the training. It's very quick to compute. You just compute the pairwise distance between this data to all the other points. Okay, next is logistic regression. Although it's called a regression, it's a method for classification. So what you have is this logistic function. Okay. You can express either in this way or that way to give you a shape like this. And then you have your data points belongs to either this category or that category. And you can assign this as a 0, 1. And this is the values you use to decide the membership belongs to which one. Then you can fit those data points, yellow and blue, with this curve. If you don't know the formula of this curve, you probably will fit that into a regression line. For example, if you don't know this, you may say, okay, I will do a regression, and I will have a straight line across that. That will not help you to decide the membership of those. Okay, very quickly, we can move to another one. So LDA is called linear discriminant analysis. So the purpose of this is to rotate your data point, okay? Pretty much like PCA. So that's why I want you to, once you learn a new algorithm, you can see I want to expand this and want to reformulate my question, maybe redesign the purpose. Like PCA is for separate data points, but here also they want to separate the data points, but these data points have two different classes. One is red, another is green. So if you do PCA, you probably will rotate to put x-axis here to separate data points without knowing they are red or green. Okay, if you consider they all same color, so you want to run a PCA, your first dimension, you probably will see like this to show the data. But if you redesign PCA and say, okay, even though you don't know how to do this, how to write the code to do this, you probably can talk with a data scientist, say, okay, I want to rotate my data points, but I want to, after rotation, I want to see the reduced dimension, after dimension reduction, the data are more separatable than before, okay? So once you can translate those language to the purpose you want and translate language to data scientists, they understand, they know how to do the rotation, and they know how to decide objective function, and they can do this for you. But you have to know the language, you have to know the purpose. Okay, so in this case, we want to find a separator to separate those data points. Let's see. This is a good example. If we don't know red and blue, we just consider that one group. And our PCA will reach to this stage to allow you to find the first PC principal component, the x-axis. in this direction, and your y-axis is probably that direction. However, if you decide our goal is to separate blue points with red point, you probably will select this as your main PC. Because after project all the data onto this first PC, they are separable. Or maybe this one is the best. This is not a very, very good example. I gave you another good example. This may be the best example to illustrate this small corner here. So the data are distributed like this. PCA will give you the answer. This is a PCA. Right? If you don't consider the labels, just think, okay, they all red or they all green. PCA definitely will give you this. But LDA, give you this. Why? Because once you project your data onto this axis, the boundary becomes larger and you can separate them. Well, if you do traditional PCA, you don't consider after dimension reduction, there are some of those data points are mixed up together. They overlap to each other. So this is a good illustration, better than the previous slide. Okay. And then you will realize the procedure for PCA, LDA almost the same. Very small tweak of those goals and give you a completely new algorithm for completely different purpose. So that's why I want you to consider the algorithm. Okay? If you have a good biology question you want to answer, and if you have an ability to translate the problem you want to solve in biology and into the data scientist understandable language, like rotate this, my objective function is to discriminate those two clusters. They will have immediately pop up a lot of algorithm off the shelf, probably just combine some algorithm, make a new pipeline, maybe just tweak some internally and to solve the problem. So this is the algorithm LDA steps. And you have your homework to describe how PCA procedure is. So this is very similar. So you have step 1, 2, 3. In 5 already have this eigen decomposition. Okay, to get the projection matrix. Basically, that's rotation matrix. All the same. The difference is here there's some within cluster and between cluster computation, because you need that information to help you to decide how you rotate the data. Well, PCA you don't have to. You just look at the covariance matrix that contains all the information that between the variability between data. Okay. But here you need some information. Just within each cluster and between each cluster, because you have predefined those labels. You learned a rotation matrix. That rotation matrix will help you to find the new axis and then project your data on, and then you can separate them. The output of LDA is this rotation matrix. So when you have new data points comes in, and you can use this rotation matrix to rotate it and see where they will project And then where the project will help you to decide it belong to red or green class. Is that okay? So this is the MATLAB code. It's so simple. All right. You have X. Remember, in PCA, you don't have to give label. But LDA, you definitely need to give label, say which data points belong to which class. It will find this PC to help you to separate the two groups of data. Okay? The object this will reach is to maximize the difference between the mean. Okay, you have two clusters, red and green. So the center is the mean, the mu1 minus mu2, and also normalized by their variability in that direction. Yeah?
Would the label be defining, like an example, would that define the cell type or the batch ID?
Either way.
Either way?
Yeah, depends on your problem. If you want to LDA to separate cells in your training data, it's different cell types. You can have a cell type 1, A, B, C. Okay, you have multiple. You have multiple.
So you would just, so what you could do is, because we wouldn't know the cell types before, is LDA considered a downstream analysis, or is it like PCA?
It's not a downstream. It's a classification algorithm, but you need a training data. Yeah, you need to have a label to. You have your training data. You have a label to learn the rotation matrix. But once you finish the rotation matrix, you know this rotation matrix will help you to predict the new data, the categories of new data. Okay, so this is a difference between PCA will project everything onto here to separate the data without considering the membership of those. And they just look at it globally, and this give you the maximized variability, but where LDA will find the separation. So consider to make the variability within the group small, but between group large. Okay, another one called Bayesian. So we use Bayesian method to assign the membership. So this is not a standalone algorithm. You can build in this idea in a lot of those problems, as long as you know how to construct prior knowledge, prior probability, and try to get so-called posterior probability. So the way how it works is like this. So we want to predict the member ID, okay, either yellow or green for these new data points. The first one, probability we want to compute is how many, the percentage of basically the probability of any given data belong to green one, how many belong to yellow one. So in this 17 data we know from prior knowledge, 7 belongs to yellow. So we have pre-knowledge, like a probability at 7/17. And we have a green is 10/17. So if I know nothing about the membership of this, it's supposed to be green because I have a more likely to be green because in my baseline model, I have more data belongs to green class. Okay, so that's a prior knowledge. Then I will decide to use some of this, for example, use KNN in the middle to look at within its nearest neighbors, and 3 are green, 1 yellow. So at the end, my posterior probability is a product of these two, okay? 10/17 is my pre-knowledge before I know anything specific about my input data. But this one is after I put the data in the cloud and look at its nearest neighbors, and that probability which belong to green 3/10. So altogether, this is 30/170. You can do the same thing to the posterior probability belongs to yellow, and that is this. Okay, then you have some, see, I have a confidence of this over that. This new data belong to green category. This is another example to decide whether an email is from a spammed email, from some attack, using those terms, okay, those words. So you build some of the words, and there are particular keywords that have a prior probability to show in the spammed email. So you synthesize those information at the end. You gave this whether spam or not. So you can take a look at those examples. Yeah, I think we need to mention how can you evaluate the performance of those classifiers. There are several ways, and those are the commonly used. Cross-validation, so CV. So people in data science, when they say CV, it's not your resume, it's cross-validation, always used. We need to know how to look at the ROC curve. Okay, you always see those ROC curve. Have you ever seen this kind of things? So this was used to evaluate the performance of a classifier globally, like how. So this is like one curve compared to another. So if you have another, this is supposed to be better classifiers than this one, okay? So how this cross-validation works. So when you have your training data, you not give the algorithm all the training data. So this all the data, you know the answer, the labeled. But you gave it like 90% of your data from training data, gave to the trainer, gave the classifiers to train it. And then you use the last 10% of data as your test. Okay, you randomly shuffle your input training data, but not give 100% to the classifier to do the training, but only give 90%, and keep 10% after train the classifiers using 90% of your training data, and then test with the 10% of data, and get the accuracy, because you know the answer, okay? So in this case, 93%. And then you do that again. You shuffle your training data again and keep 90% and give 10% as a test, and then evaluate 90% accuracy. You do this 10 times, okay? And then you average this accuracy. You get the averaged cross-validated accuracy of your classifier. I know some people use not 90%, 10% ratio. Sometimes they use 80% training, 20% test. It's okay, I believe. I don't know what's the most commonly used is. Depends on how many input data, training data you have. Is that okay? Simple, right? The training data probably you have to label manually yourself, just like last computer session, and I showed Michael in the nutrition department. He used his knowledge to assign the cell type. He used marker genes, yeah. So after you finish your manual label, you can use this data set as your training data to train the classifiers. So once you have a classifier ready, next time you don't have to manually do this, and you just gave the classifier, automatically should give you the answer.
But first, we just choose the marker gene and I don't know, we separate.
Yeah.
But how we do that? We just choose this marker gene and.
Yeah, because he know what the cell type he's supposed to see in his sample.
But you need to know which cell type has that marker gene.
Yeah.
Or the machine
No.
Oh.
Yeah, he knows which marker gene. Yeah. Yeah, EpiCam is such a clear separator. Yeah, he used manual annotation. Yeah, yeah. He didn't use any of those classifiers. Yeah. Yeah. So confusion matrix is so how many cells, for example, you predicted those are real, and how many real you predicted correct. So this is the true positive, and you have a true negative, and so this is like a binary classification. So yes or no. So you have your data in the training data. You have all positive ones have been classified as positive, or the negative being classified negative. That's a perfect separation. But if you have some numbers in these two corners, as false positive, false negative, you don't want to have large numbers in these positions. And that's once you have those data numbers, you can compute the precision or accuracy. Okay, so let's also have a recall and power, sensitivity, specificity. So this all can be computed once you have this 2x2 matrix. Okay, right? So this one, you can use this one to evaluate the accuracy of your classifiers, right? So this curve, when you see this curve, you want to compare the performance of one classifiers with another. So I have this pink and this light green results. And in your x-axis is false positive rate. On your y-axis is the true positive rate, okay? But normally people write in different way. They use 1 minus specificity, okay? So this is also 1 minus. Or this one, the power probably is called sensitivity here. It's confusing. Sometimes people not use 1 minus specificity, but they just use specificity. In that case, you have to put 1 here, 0 here, the opposite. But anyway, so eventually you look at the curve and to measure the area under the curve. Okay? So the area under the curve for the pink is this, while under the curve for the green is smaller. So in that case, the performance of the pink algorithm is better than green one, because under the curve area, pink one is larger than green one. So what that means is this curve was constructed using a series of dots, a series of points. You know how to compute specificity, you know how to compute sensitivity. What you can compute this, you can use the confusion matrix, right? So each time you test so your algorithm, your classifiers, through your test give you the confusion matrix, right? And using the confusion matrix, the 4 numbers, you can compute sensitivity and specificity. You can compute these 2 numbers easily. So you put your number in here. So this is one single number, right? And then you can see this classifier. I will test again using different parameters. I change a little bit, or probably can test using different training data. I label different. Again, you get another confusion matrix. Right? Then you can compute these 2 numbers and label onto here. So you try a series of testing by change the parameters, by change the input training data or testing data. You get a series of values and make a curve. So this curve shift to the upper left corner here means no matter how I do this, I will normally get high sensitivity but a relatively low false positive rate. Okay? Or in this corner, when you have 1 as a specificity, you have in this corner is high power, high sensitivity, and also high specificity. That's the goal. We want to have an ideal classifier, right? So that's why when you see a curve goes to that direction, it's a better classifier. Compared to green one, it's always have low power, low specificity, that to that direction here. If you have a purely random classifier, just randomly assign the labels, you should have this curve which is right on this diagonal position of this line, or just shift a little bit maybe. So this is the way you calculate ROC curve, and how you rate ROC curve. It's very important to use this to visualize or quantify the performance of the classification algorithm or classifiers you define. Okay, single cell classification tools we actually used we don't use them, okay? Because it's harder to train, and we don't have a golden standard to see, okay, I can train the classifier using a lot of data, and then we are done. It's never the case, because you fine-tune the parameter, train a model, but next time you have a batch difference, you have a slightly different reagents, and you generate a matrix. The feature is very different from the one you used as a training. And also, probably there are performance problems. So you have you test this and get very poor performance. So normally people just don't use supervised learning algorithm to do this single cell data training. Certainly, a lot of algorithm has been tried. For example, those are examples. Data scientists have been tried to do this, but eventually we stop using them. So you never see, I don't know whether this single R, I've seen someone using it, but it's clusters, Spearman correlation. So it's not a very typical machine learning classification algorithm. But those, there are some of those. There are another list of the automatic cell identification methods. Those are the package names. Okay, they are different versions, and in R or Python, this is the algorithm they use. You can see LDA has been used. Okay, random forest, KNN, neural network cell-to-cell similarity. Okay, I hope this review can help you to get some idea. So this is which year's review? Automatic. Questions? Questions? No? This is like a overview of this prediction algorithm. Let's see, SC predict. So this method. Let's see what SC predict. Yeah, so the algorithm that used is SVM, as we will mention next week, and some kernel. So this is another called the single cell net. Building the classifiers, we need training data. Yeah, so this uses random forest. Okay. Also, we want to use the standard, for example, random forest. I didn't mention random forest at all today, but next week we probably will touch base on some of this. But they try to build into this algorithm using additional information. For example, we want to use a gene-gene interaction network to help do the classification. Okay. This is an example of manual annotation, and the sum of paper just say, okay, we don't use any classifier. We just manually found to look at those marker genes expression in your data. This is probably the best way, and so far, I believe. In the toolbox, we use a method in dbScan. Okay, there's some description in this paper how this cell score based. So this is not score based. So this algorithm uses marker gene database to compute a score for each individual cell. Not only one score, but all the scores. So if you have in the database have 120 cell types, this algorithm will compute cell group. You can compute the individual, but the group. For a group of cells, for that particular cluster, it will compute, say, 120 different cell types. It will compute 120 scores. And then pick the higher score to assign to that particular cell type. It uses marker genes, also the expression of marker genes. We can go over the details. Sometimes I open the source code to look at it. Okay. Yeah, so it's a time for break, and Kadaga will give us an overview for the neural network next hour. Let's take a 5 minutes break. We come back at the 8 past 11.
Hello, everyone. My name is Çağatay Bal. I'm a visiting scholar from Turkey. I was about to finish my PhD, but in order to get this opportunity to come here as a visiting scholar, I have to pause my PhD. And I was basically, practically, at the end of my PhD. But I can, describe myself as an enthusiast of artificial neural networks. So today I will talk to you about what is artificial neural networks, why they are so marvelous, and where they come from, basically. So I want to keep my presentation as funny and as a storytelling somehow to be, to make it not boring for you guys. So let's start. Let's start with some basic things. So what is algorithm? We always use this algorithms and talk about it. So, but I like to keep things, to discover where they're coming from originally. So, the algorithm is like a set of instructions for solving a problem or accomplish a task. So it's like a step-by-step procedures we just follow, basically. And the most important thing is here is like they are deterministic steps. So there is no stochasticity or not randomness in the algorithm steps. It can consist of some methods or some approaches consist of randomness or stochasticity, but the algorithm itself is like deterministic, step by step, just a road we walk to solve a problem. So, originally, is anyone know this guy? This guy is a great Muslim philosopher and scientist by his time. So he's basically the inventor of algebra, what we know today. And if you can see the name, actually Al-Khwarizmi algorithm, you can match the intuition. So basically this guy has invented what we call algorithm, and it's basically his name. So, and this guy is really, really old. So after that, I want to talk about what is heuristic and meta-heuristic. Since last week, we with the presentation of Louis, we started to hear about the heuristics and meta-heuristics, but what exactly they are. So the term heuristic means, and originates from Greek, actually. The word heuristian means to discover, to find. So it's really closely related to the idea of I'm sorry, it's about some version thing, I guess, because it shouldn't be appear like that. I'm really sorry about that. But it's practically about problem solving. So when we call heuristics, we are talking about solving a problem. So this is so important about critical thinking, the questioning, and exploring the pursuit of understanding. So what I call is simply the art of problem solving. So when you go down to philosophy part of the heuristics and this algorithm things, you end up with like, describe it like the art of problem solving. So when you do your art better, your problem solving becomes better. So in mathematics, the heuristic means that when you don't need any proof or lack of proofs on problem solving, you become your your solutions become based on intuition, the trial and error, and empirical observation. So it simply means like you use your instincts, your natural way to come up with a solution of the problem. So this is our solution space or search space, as you already familiar with last week's presentation. So basically, we start somewhere on this space for our daily basis problems, anything else you can imagine. Because in real life, all of our problems are nonlinear. There's nothing linearity or nothing that simple to solve. For example, like after the class, we just go out and do our daily routines or some shoppings and some rules or some meetings, etc. And we end up at the home. So along on this way, we can come up so many probabilistic things that can occur, and we cannot just model it. We just non-linearly, intuitively just run over all the problems, and we end up with the local optimal solutions. So there can be a global optimal solution for our daily basis problems, but it's non-linear. So 99% of time, you cannot achieve any global optimal solution, and you don't have to. So we just come up with the very fast, very satisfying solutions close to global optima. So local optimals are the only way to go in the real world scenarios. And I will say many things about the solution space later on. So it's really important about the artificial neural networks and heuristics and optimization. It's all about it. So what is the first heuristic? Okay. I will talk about the Babylonian method. So it's really easy, and it's the first heuristic. Let's say we want to find the square root of n equal to 17. So the first is making an initial guess. So intuitively, we say just, OK, let's take x as 4. Why? Because the square root of 16 is equal to 4. So it makes sense to just start from 4. And at the second step, we just try to improve our guess with this basic formula. And when you calculate this one, you come up with 4.125. OK, let's the heuristic says do it again. Do it again. And the second time, 4.123. And the third time, 4.122. So it decided to, decided to stop here because it's really getting closer to the optimal solution, what we can call global optimal. But this local optimal is satisfying. So we don't need to try harder and take so much time to get the actual square root of 17. This is also the will do so better in a very short time in a very simple way. So do you think when this algorithm is published or discovered, any idea how old is it, this first heuristic? No? So this is basically a clay tablet. It belongs to the Babylonians. So it's like 17th century, but it's before century. So this first heuristic is like more than 3,700 years old. So the heuristics is like very, very old because the problem solving is some natural thing. So long before our supercomputers or basic computers or anything about the math, is just the heuristic starts the first. All right. So what is meta-heuristics? Okay, this meta-heuristic is a higher level algorithm frameworks. Basically, heuristics are problem specific, but meta-heuristics is a general purpose. So this is the only thing dividing these two things altogether. So meta-heuristics are general problem solving strategies. This focus on exploring and exploiting the solution space. You remember our solution space? So we just trying to find the good solution while searching all the space. So Louis already gave so much information about the meta-heuristics, but there's plenty. So I can say anything about the animals can be mimicked, can become a meta-heuristic algorithm. You can see the ant colony, artificial bee, fish swarm. There's even gray wolf, cuckoo search. So there's so many. So anything about the natural can become, any meta-heuristic algorithm. Okay. So why animals important for optimization? I have a simple word that can describe, and it's like I will get your guess. So in its most fundamental sense, refers to the continuation of life, and despite various challenges. Okay, I even cannot read it in this form. Sorry. So to sustain the health and the continuability. So I just described this question, why animals are important for optimization, because it's the perks of survival. So what are the perks of survival? It's like I can easily describe it like adaptation, problem solving, and dedication. So when you have these three perks, you can come up with any idea or any algorithm, any meta-heuristics, any method to solve a problem. So the key thing is natural, becoming the nature. So mimicking the animal behavior works. Also, if we can, I can give you more. I can add you. Add to this table more and more and more. So it can be seen really crowded, but believe me, it's not. There's plenty more. So the thing is mimicking the animal behavior, or natural behavior. Okay, I will give you a specific example that I find the most funny and interesting. So this is Tokyo train network. So it's basically have the major points and the cities and the routes that merging all together. So do you even guess how many years or time that the scientists or employees that come up with that optimal network of the Tokyo city? I don't know the answer, but I guess it took years and years. But there is something you can see in here, and this is the name. I believe you are more familiar to biological stuff than I do. I cannot even read the properly, but it's a single cell, brainless, yellow mold. That's all. And it has an ability to build highly efficient networks of nutrient channeling tubes between food sources. So this single mold can create a network between food sources. So some scientist guys come together and try to use that mold to recreate this Tokyo train network. So this is the result. It's so interesting for me for a single cell mold. So just after 26 hours, they come up with better solution as well as it's really good optimal solution for Tokyo. So they just put the food sources to the major points of the city, and they come up with a network that really do amazing jobs. So this is only animal with only one cell. So imagine what we can do with the more intelligent animals. So I will ask which is the most intelligent animal as far as so many people can consider is just, we can say humans, right? So which part or property of human we supposed to mimic to create a method to make it more intelligent? So as we can say, it's brain, human brain, and this is the neuron, the very basic particle or cell of brain. So you know better than me. But when we mimic the shape of the neuron and its properties, we come up with the artificial neuron. So this artificial neuron, like dendrites of the original ones, receive the data from previous source, and then in the soma or cell body, it just processes this information, and with the axon and the terminals, it just, and snaps, I don't know, it just spread the information and make it output to another neurons or just simply out of the system. So this is the basic idea of the artificial neuron. But what is inside an artificial neuron? So basically, there is a processor unit. It's so simple. It just multiplicate the input information and the weights, what we call. It means it just gives the ability to make it intelligent to hold the system, because these weights are the components to decide whether this particular inputs are important or how they get into relationship with each other. So at the core of this artificial neuron, we just multiply these x's and the w's and add the bias. This I will talk about a little bit more. And then we sum of it and then create an output of this neuron. So this is all we are doing at the very basic form of artificial neuron. And let's talk about the first artificial neuron. So before perceptrons, in 1943, actually McCulloch and Pitts just introduced the first artificial neuron. So this neuron doesn't have any intelligence, doesn't have any cool stuff going on. It just multiply inputs and weights and create a sum, and there is a threshold, not even a function. It can just able to produce a binary output. It's 0 or 1. So just a threshold. There is no learning going on in here. But it just creates a spark. So after like more than 10 years, it's 57, yes, the perceptron is published. And this name also, this perceptron came as a name as a linear classifier. Because there is a, okay. So after the first neuron, the perceptron adds what we call today's activation function. So this functionality is a first crucial component to the artificial neurons, because it just leads to what we call learning today. So without activation function, we cannot teach anything to artificial neurons or artificial neural networks. So this was a primitive version, of course, but this activation function enables to produce an output continuous rather than zeros and ones. So this continuous output will make us create an algorithms and do some heuristics to give this system intelligence, what we call intelligence, the primitive version, but it can start learning somehow. All right. So let's continue. Yes, perceptron learning rule. The second thing after the activation function is a perceptron learning rule. So what are we doing in here? Perceptron can learn from this from its errors at the output step. So when the perceptron produces an output, we can calculate an error and then use this error to update our weights. So how we do that? And also it's like basically the first learning rule, and the first term we are using today is supervised learning. It's the first example of what is supervised learning back then. Okay. So I want to demonstrate a simple example of what's perceptron learning. Let me just grab a pen. Okay, let's consider we have a 3 points of observation in the coordinate system. So let's say this is class 1, and these are class 0. So what we want to do is like creating a line after all the procedure to separate these two classes altogether. So this is the main purpose of perceptron. So how can we do that? Okay. So for this particular one, let's say it's 1.3 and 0.5, and for this one, okay, 2.5, 0.6, and this one, 1.8. And 3.4. So let me draw our perceptron. Okay, this neuron is for our x coordinate, and this one is for our y coordinate. And when we describe these coordinates into perceptrons, we have to show like a vector. So our x coordinate and this particular neuron is like x1 equal to 1.3, 2.5, is it here, and 1.8. So for this ones, I basically call it x2. The second input is 0.5, 0.6, and 3.4. Okay. So in every particular neural networks or neurons or perceptron, whatever you do, before you start your process, you have to initialize your first weights. So this based on most of the time randomly. So when we just randomly assign 0.2 to our first weights and 0.7. And for the bias, so I will just assign 1. So the bias is basically like a degree of freedom. It adds the degree of freedom, because without bias, our line have to go all the way through origin every time. So we cannot draw like this any line. So without the bias, our lines have to cross to origin every time somehow. I don't know. Whatever you come up with, any x1, x2, anything, but without the bias, you cannot draw line over here. So it has to be cross the origin. So that's the main idea. It's like a degree of freedom. So it's a little boring, I know, but just show the first equation in here. Okay, less in here. We just calculate the sum. So for the first for the first class, this observation, we just do this multiplication and sum. And it gives us 1.61. So it's a positive. So this is class 1, so it has to be positive. So we assigned it correctly. So our perceptron rule assigned this class as we label it. So it's a succeed. But for the second point, when we do the calculations, it also come up 1.92. So it's positive, but it should be negative because it's a class 0. So it failed to assign the correct class of this particular observation. So we have to update our weights in order to make both of them into same label or the same cluster. So iteratively, it just works like this. We have to calculate our error. So what is this error? So this is misclassified. So it has to be at the class of 0. Our error equals to, it has to be class 0, but we predict it as a class 1. So we just divide, make the summation. So we come up with the -1. So what this means? It just says let's change your weight according to your findings. So our new weights become like this one. The previous value minus because of the our error divided by multiplied by this particular value of the observation. So when we do that, we come up with minus 2.3 as our new weight. So when we do that like 7 or 8 times, we come up with the optimal weights that can satisfy all the observation into particular correct class. So that's basically what's perception rule, perceptron learning rule is. You just iteratively use these heuristics and do it again and again and again to find the best values that can draw a line to classify these two sets. So I know it's boring, but I wanted to show what's really is a perceptron rule. So, but there's a thing happened way back then because the generalization of the perceptron to the multilayer version, because it's just a single neuron, it didn't well because they didn't come up with a better solution or to describe the generalization of this rule. So it just tends to not work. And they just published some other guys just published a book named Perceptron. I particularly have this physical copy. This book is all about blaming how perceptron doesn't work. So they just wrote a book to show, to blame a method that it doesn't have any potential, no time to waste to go through in any advanced form. So it just creates what we call the AI winter. So it just like 20 years of unfunding and uninterest area. It just stopped anything about the AI, what we call AI today. So it basically, the idea was XOR or exclusive or logic gate. So this is an important testing to a new method. So when you come up with a new method, they were just tend to test it with the XOR gate. So in the XOR gate, it's simply there's a two class. I'm sorry. You can describe. And for linearly, it's just impossible to divide these two sets. So whatever you draw in here or like this, anything, you cannot just make this classification works. So you have to draw at least two lines. But the perceptrons cannot draw two lines with only one neuron. So this limitation and the poor generalization, the idea, led to some guys just write a book to how it won't work. So it will end up 20 years of non-development. But the savior of AI is based on this Nature article that published in 1986. It calls backpropagation algorithm. So it makes what we call intelligence today. It's based on that particular algorithm. So this algorithm can give the ability to learn to neural networks. But it's actually based on this method is based on the PhD thesis by VIBS in 1974 in the Harvard University. They just come up with the idea of this particular thesis, and they just do it so well and adapt it to the neural networks. So maybe you got the second name is the Hinton. So we will be hearing this guy's name so much because the Hinton is like describing as in the community as a godfather of AI. And maybe if you remember the Tsine, the function, which is embedding, okay, this was the guy that published that paper also. The Hinton is important. So what's this backpropagation? Simply, we now have our multi-layer perceptron. We got another layer, which we call hidden layer, and many neurons, they just connected all together to communicate and accomplish many advanced nonlinear functions to solve. So basically, we just calculate the error at the end. This error is described as sum y hat square. So this forms is our error. So this error, by this error, we just can use backpropagation algorithm to backpropagate this error to the corresponding weights of each neurons we have. So, like let's say when you take a derivative of this error into any particular weight, like this one. So with this particular derivative, we can calculate the new Wi with this formula. Like, okay, this is a learning rate. Let me proceed. With the gradient descent algorithm, of course, the Louis described us so well at the last week. So with this learning rate, basically do these jumpings how close or how far. So that's basically this parameter is what is it used for in the gradient descent. But in the backpropagation, in a very simplest form, we take our error, and when we take a derivative to the corresponding weights, we can come up with the new weights. So new weights means more closer to optimal one. So after iterations and iterations and iterations, when we do it so many times, like calculate all the information, like everything at the end, produce output, calculate error, and then backpropagate it. So each time we do it like 1,000 times, I mean hundreds of times the iterations, and after that, at some point, we just come up to very optimal or local optimal solution with the backpropagation algorithm. So that's the main idea. But it just do it so well, and after 1986, it just started. But before proceeding, so I want to ask you why some of the squared errors? Why we use this form of error every time? So do you have any idea of why we take this particular form and we call it error? Why we have the sum or squared? Any idea? No? Okay. And also, the second question is the notion of minimizing errors origins from where? It should be coming from somewhere, not in the backpropagation algorithm or gradient descent. It should be old, I guess. So the first thing is the positive definiteness. So to prevent the cancellation of negative and positive errors, we just take a square. We can use also absolute 2. It can be worked, but when we want to emphasize the outliers, so taking a square is like a better than the absolute form, because when our error is becoming larger, we will penalty them. We will emphasize them more in this squared form. But the third thing is convexity. So this convex thing is really important because in the convex form of any cost function, this can be called cost or loss function, by the way. It's a convex form of any particular optimizer, for any particular optimizer. It can be solved and can be found global optima. And so basically, and obviously, it's the differentiability. So in order to find that form of information lies under, we have to come up with the loss function that we can differentiate. So these 4 perks are the main reason that we use this error form, the function. All right. So you guys know linear regression, right? In the linear regression, we use a method, actually what we derive from this minimization thing. So it's called least squares. So least squares is basically the oldest idea of using error and in this form, and then taking the derivatives and make them equal to 0 and find out the minimum points of the curve. So it's like 1800s or something like that. It's really old, but everything about this algorithm learning, the AI, and depends on least squares and this idea to using this error to train or teach any mathematical function, anything. All right, so after that date, I just call it stairways to AI heaven, because we now come up with the very potential way to create any system that can learn. So this is basically what we call multi-layer perceptrons. There's multi-layers of neurons, and the components are basically the neurons, first of all. These are the processor units. We do all the calculation in these dots. And the weights. So the most important part is the weights. So the learning means finding the optimal weight. So basically that's it with the neural networks. Activation functions make it adding to ability to learn with the nonlinear functionality. So without activation function, the information just vanish. So it's a crucial part. So layers. Layers also make it more complex form and advanced form to handle the very complex problems. The bias is, like I said, is a degree of freedom, so it's really important. The architecture is what we call this scheme. So in the neural networks, there's a plenty more different architecture to serve different purposes. The loss function and optimizer is really important, and the main thing we use is like this error and the gradient descent with the backpropagation algorithm. Okay, so this weight initialization. Okay, let's talk a little bit. It's about my PhD thesis. So the weight initialization at the neural networks is start like randomly at the first, and you just come up with the optimization process to optimal weights. But what if we just can compute weights somehow, rely on our data to start very good position in the search space rather than any random point? And I come up with an idea and create a method relies on the probability density of a given data, and I can calculate the nonlinearly density function and use that information to assign weights rather than randomness. So it worked, and it somehow make this optimization process so fast and easy, because it just start really near to local or global optimas and end up with the local or global optimas in very short time. So this is basically the idea. Okay. What we call learning. Learning is, oh my God, I'm talking so much. Okay, learning is like what is about the neural networks. It can learn anything. So supervised learning, we just learned today. We have the input-target pairs. We just show the initial method that you have to reach that point. So this is our targets. And reinforcement learning is like there is a reward or penalty mechanism within the neural network. So when neural networks in the learning process achieve some good things, it just rewards itself. So when it rewards itself, it just tends to go that particular route on the optimization process. So this is what we call reinforcement. And unsupervised learning, we just got our input data, no guidance, no target value, no labels. It just starts to form an information out of that. So there's plenty of different types of neural networks. I introduce perceptrons and feedforward neural networks, but there will be recurrent ones, autoencoders, and it will become a deep learning, what we call deep neural networks. It goes and on and on. So with the feed-forward neural networks, this is also known as the universal approximator. This is an important point because with neural networks with one hidden layer can learn any nonlinear function. It's just you can do any regression, classification, tasks, function approximation, pattern recognition. The time series forecasting is like my main area. Anomaly detection, dimensional reduction. You can just add. Okay, let's pass that. Okay, the autoencoders. The autoencoders is what I call the magicians of AI. The second great invention of the Hinton, again. So this is the first neural networks that can learn unsupervised. So the most famous application area is denoising. So when you give a noisy input, it just makes it so clear. So basically, the best application area and the best idea under it is like there's no labeled data. You just give your noisy input, and it makes it clear for you. And convolutional neural networks, I call them the eyes of AI. So you can teach any image-related data to convolutional neural networks, and it can just recognize it. So it is basically what we call image recognition. And in the convolutional neural networks, there is a convolution and ReLU layers with pooling. So Dr. Tsai is also showed us a video, but just give me a very fast example of how it really works. Okay, let's say 1, 5, 9, and 20. So do you think how we just, how convolutional neural networks read a picture? So we have to somehow consider it like a data. So actually an image has a pixel values. Like every image has a size of, let's say, 100 by 100 pixel size. So that means that means a matrix like 100 columns and 100 rows. So each cell of this matrix consists of a pixel value changes between 0 to 255. So you can just, with the convolutional neural networks, when you give an input of any image, it just converts it to this matrix. It's basically all. It's not a so complex thing. So it just converts this image to this matrix. And what pooling is done is, let's say we have a window. It just goes through all the cells of this matrix. And it just took the max values of 4 by 4. So let's say it max pooling in this layer, particular layer, in this particular form, like let's say the first 4 cell of this matrix, it just took 20 as an output. So when we do that, after time and time and time, we just got the abstract information of our particular image. So when we do it 1,000 times, it just learns the abstract form of every single image. So it becomes so complex. As you can see, there's more different connections, layers, and stuff. So after that point, the guys in the communities like come together and they just said, okay, let's build a network and train it with the millions of images and let people use it. So basically, it becomes the idea of the AI scene. So there's a very famous convolutional neural networks that you can use. So the next one is long short-term memories, the LSTMs. I call them writers of AI. It becomes more advanced and complex form. This is basically just single neuron. Rather than just multiplying and summing, there's so many things going on. So it just becomes so complex. But there's a Sunspring, is a short film. And after training the LSTM with thousands of scripts and scripts, it just produced a script and it's a short film. So the script is all written by the LSTM. Nothing human involved. So it's a good example. Okay, the next one is the GAN, the generative adversarial networks. I call them the wizards of AI. The idea is so simple. There's two neural networks. The first one is discriminator, and the second one is generator. It's the first neural networks that uses the noise as an input. So discriminator is like a simple neural networks that we just trained with known data, but the generator starts to trick the discriminator by producing images from noise data. So after thousands of iterations, it becomes like generator can trick the discriminator. What we end up, we just can learn the landmarks of any face, so we can just embed it to any images that we want to. So it just make us able to create some images, some peoples that never lived, or this just digitally created, but in a very perfect form. So after that, it's just diffusion networks. It just become more complex, and this is the diffusion networks, the alchemists. So basically, it's just text to photo, text to image AI. So this is the staple diffusion is like 2022, very famous one. It just took the guys to train this 1 billion parameter network to train with the cost of $600,000, something like that. But it just creates just fake but perfect images from noise data, and it becomes so complex over time. And the transformer of networks, I call them the maestros. There's so many things going on in here, embedding inside feed-forward neural networks, and so much things going on. So basically, just encoder and decoder, you just give something, and it just shifted something that's meaningful for you. Okay. The very first famous transformer networks is ChatGPT, as we all know. So the idea is like it becomes like important to prompting how to use the AI. So prompting the AI rather than creating an AI. So I just can say that nothing yet about the single cell, but when I just prompted like how can I design a process to analyze RNA-seq data in raw format without any processing steps with any type of artificial neural network. So it gives me some idea to start with, basically. Maybe it can work, maybe not, I don't know. But when I proceeded, is there any published study? So it gives me some papers. So if you learn how to work with the AI, how to use it, it will be more making sense than try to create an AI. Because there's some companies right now with the infinite sources and people and money, so they can create so much cool AI. So it's better to learn, how to use them, I think. So I just asked a simple question to ChatGPT. Is the ChatGPT based on neural networks? Yes. BART is basically Google's AI. The answer is yes. Face ID, yes. Alexa is Amazon's, yes. Duolingo, yes. Tesla's autonomous driving based on artificial neural networks, yes. Netflix AI, yes. So basically, AI means artificial neural network. It's not like a scientific, science fiction thing. Just basic neural networks. So do you happen to heard about Sora lately? Anyone? It's amazing, right? It's like a text-to-video AI. So we don't have time, so you can watch it. So you just type a prompting, just give me a mammoth running, just creates a video. So it's amazing. But I doubt that they will, make it published. I don't think so. So lastly, okay, the final thing, what it will go is artificial general intelligence. So this is the next step. Everyone is pursuing that, like Elon Musk, like Zuckerberg. And also, I just asked the ChatGPT that, can you summarize a single sentence? Would Apple Inc. already achieved artificial general intelligence if Steve Jobs alive? So